All right, we're at, I think it's 16.8, the intensity of sounds, and there's a few sections in here. Probably going to go through this math fairly quickly because get down to uh, the main equation. So here again, we have our piston that we've seen throughout these lectures, and power is equal to the force times the velocity in the x direction. Um, the uh, velocity is uh, distance divided by time. So force times distance divided by time is power. Force times velocity is the same as force times distance divided by time. Okay, so the power is equal to the change in pressure uh, as a function of x and t times the area dotted with the partial uh, of s x t in the I direction, delta partial of t. So PV omega area times s. I said p. It's rho v rho times the velocity times omega times the area s max sine kx minus omega t times the partial of S max cosine kx minus omega t equals the rho v omega as max sine of kx minus omega t. And with the partial, you get omega s max sine kx minus omega t. The derivative of cosine is sine. And so you end up with rho v omega squared a squared sine squared kx minus omega t. Uh, so the 1 over t, the integrated from 0 to t of sine squared 0 minus omega t dt is equal to uh, 1 over t integral 0 to t sine squared omega t dt. Um, and so that's equal to 1 over t, t over 2 plus sine 2 omega t over 2 omega. Look that up in the integral table. Evaluated from 0 to t, you get 1/2. Um, so the power is equal to 1/2 uh, rho times the area omega squared s squared uh, s max squared times the velocity. So the intensity is equal to the average power divided by the area. So the intensity, you can see there's an area in the power equation. So the intensity is 1/2 times the density times omega squared times S max squared times the velocity. Um, so the uh, intensity is equal to the delta P max, the pressure squared divided by 2 times the density times the velocity. Now, the sound waves, we've been working with this cylinder, which is all in the x direction, but sound waves go in a spherical wavefront. Here's an image. The rays are radial lines pointing outward from the source, perpendicular to, excuse me, to the wavefronts, and it's a spherical wavefront. So the intensity is equal to the power, the average power divided by the area. So that's the average power divided by 4 pi r squared. That's the spherical wavefront. Okay, let's look here. The vibrating guitar string makes very little sound if it is not mounted on the guitar body. Why does the sound have greater intensity if the string is attached to the guitar body? The string vibrates with more energy. The energy leaves the guitar more rapidly. The sound power is spread over a larger area uh, to, at the listener's position. The sound power uh, is concentrated over a smaller area at the listener's position. The speed of sound is higher in the material of the guitar body. None of these answers is correct. And the answer is B, the energy leaves the guitar more rapidly. It's the large area of the guitar body sets many elements of the area into oscillation and allows the energy to leave the system by mechanical waves at a much larger rate than the thin vibrating string. Okay, so we're gonna discuss sound level in decibels. And the decibel here expressed as beta is defined as 10 log, the log of the intensity divided by intensity zero, the minimum density, which is the threshold of hearing, and it's 10 to the minus 12 watts, 10 to the, so for 1 watt, beta is equal to 10 log 1 watt per meter squared divided by 10 to the minus 12. That's your I0, 10 to the minus 12 watts per meter squared. So it's 10 log 10 to the 12th is equal to 120. Well, the log of 10 to the 12th is 12 times 10 is 120. So it's 120 dB. So here are some sound levels in dB. A nearby jet airplane, 150 decibels, a jackhammer or machine gun, 130 decibels, a siren or a rock concert is 120, a subway or a power lawnmower is 100, busy traffic 80, vacuum cleaner 70, normal conversation is 60, mosquito buzzing is 40, a whisper is 30, rustling leaves are 10, and the threshold of hearing is 0 dB. That's the 10 to the minus 12. That's our threshold of hearing. Now, a word about decibels. It's a logarithmic, and so 3 decibels is a doubling. If you increase something by 3 decibels, then you've doubled the intensity. Okay, let's see. It's showing you here the threshold. That should be a minus 12, I believe. I didn't correct that. I'll try to correct it on uh, the uh, the uh, the slides. Okay, increasing the intensity of a sound by a factor of 100 causes the sound level to increase by what amount? Well, what is 10? What is 100? It's 10 to the 2. So if you increase it by 10 to the 2, it's a 10 to the 2 over 1, that's the log of 100 is 2 times 10, that's 20 dB. And there you go. Okay, loudness and frequency. You can see uh, the threshold of hearing is this is down here. Thunder overhead, jet engine. These are infrasonic frequencies, sonic frequencies, ones that we can hear, whispering speech. This is the threshold of hearing. You can see how it varies with frequency. Motorcycle, car horn, rock concert, rifle, and ultrasonic frequency, bats. You can see very high frequencies. It's this here is the threshold of pain. Uh, in underwater communication, there's just you can see that, uh, especially like here, the threshold of hearing. It depends on the frequency. Okay, and that's it for this section. We'll go on to the Doppler effect next.